Right, ladies and gentlemen, this is the first video of 5 on chapter 5, which is radians. If you look, you can see the objectives that we're going to cover through these 5 videos. So the first objective is to convert between degrees and radians and apply these to trig graphs and their transformations. We need to know exact values of angles measured in radians. We need to find an arc length using radians, find areas of sectors and segments using radians, and solve trig equations in radians, and use approximate trig values when theta is small. So this first video is 5.1, and this just deals with what is a radian and how we can use it. So far in your mathematical education, you've always used degrees to measure angles. But like many measures, we can use different units. So for length, we can use kilometres, metres, centimetres, inches, yards, cubits. And for degrees, we do have another angle measure that we can use called radians. So you can see it says at the top there, 1 radian is the angle subtended at the centre of a circle of radius r by an arc, which also has a length of r. So if you can see in the diagram, you can see a circle, and that circle has been split into sectors. And I've taken out one of the sectors, and you can see that the sector I've got here has 2 radius lengths labelled r, and it has an arc length. The arc length, of course, is part of the circumference, and if the arc length is the same length as the radius, then the angle centre is 1 radian. Just 1 radian. Now, 1 radian is approximately the same, 1r is approximately the same as 57.3 degrees. The symbolism we use for radians is, as you can see, either a superscript r, you can use a superscript c, and the c stands for circular measure, or if the angle contains pi, then it is in radians by default. Now if you look, if I take my circle and I split it into sectors of the same area, you can see I can fit just over 6 sectors into that circle. And in fact, I can fit in 6.283185, and it carries on forever, sectors into that circle. Now, you might not recognise that number, some of you might. That number is actually 2 pi. So 2 pi radians fits into a full circle, and so 2 pi radians equals 360 degrees. Now that means that we can change from radians to degrees and degrees back to radians. So let's have a little look. So convert each of these angles into radians. So to convert degrees to radians, we use the conversion multiply by pi over 180, or 2 pi over 360. Quite a useful little conversion to remember. If you stop the video, you can convert all these questions into radians and then check your answers with the model solutions. Second set, we are converting angles, these angles given in radians, into degrees. Now you'll notice on the video we've not put angle measures on some of them. Now they really should have little r's or little c's on to indicate that they are in radians. Of course, the ones that have got pi in are radians by default. The ones that aren't, say for instance this number 2 here, which is 4.321, is in radians. Thing is, if it was in degrees, 4.321 degrees is a very small angle. We don't tend to deal with small angles in degrees. So to convert radians to degrees, we multiply by 180 over pi, or multiply by 360 over 2 pi. Again, this one says convert each angle into radians, so the conversion is multiply by pi over 180. The last bit says write down the exact value of sine of pi over 3, cos of pi over 4, and tan of pi over 6. Now you can use your calculator to help you with this, but it is very, very important that your calculator is set in radians. You can see the angle is pi over 3 for the first one, which is in radians. If your calculator is not working in radians, in other words, your class whiz hasn't got an R at the top, change the angle unit to radians and it will give you the answer. And again, you can check your answer with the model solutions. Now, since radians are just another way of measuring angles, we can do everything that we've done so far with degrees with radians. We can draw graphs, we can use basic trigonometry, SOHCAHTOA, we can solve trig equations, we can do sine, cosine rule, angle of a triangle. But it's very, very important that your calculator is working in radians. So you might be wondering why we bother using radians at all. In mathematics, there are certain things that will not work in degrees. We use radians because sometimes it makes our calculations easier. If we're doing approximations of trig, we have to be in radians. Differentiating integration doesn't work with trig unless it's in radians, and we'll discuss that later on in the course. And if we use circles, it can make our life a lot easier because, of course, radians is to do with pi, and a lot of our circle formulas have pi in it. So the first thing we're going to look at is the graphs, and here you can see we've got our standard graphs. So we've got the sine wave. You know the sine wave in degrees. Sine wave, maximum value 1, minimum value -1. And the wavelength of a sine wave is 360 degrees. But if we're working in radians, one sine wave will fit into 2 pi. It will cross through the x-axis at pi, the origin, minus pi and minus 2 pi. And of course it will reach its maximum at pi over 2, minimum at 3 pi over 2, minimum here minus pi over 2, and maximum at minus 3 pi over 2 and negative 3 pi over 2. Same with our cos wave. You can see maximum is 1, minimum -1, and again one wave fits into 2 pi, minimum at pi, pi over 2 crosses the x-axis, 3 pi over 2 crosses the x-axis, negative pi over 2, minimum negative pi, negative 3 pi over 2, and negative 2 pi. The last one, of course, is our tan wave, and we can do our tan wave. Tan wave, of course, has asymptotes. It has one asymptote at 90, which, of course, is pi over 2 in radians. Has another one at 270 degrees, which is 3 pi over 2. Has another one at negative pi over 2, another one at negative 3 pi over 2. And then we can draw a tan wave and another tan wave. Looks a bit like this. And then what we can do is mark where our tan crosses the x-axis. We'll put those values in. Just put those in red. So negative 2 pi. This is negative pi, 0, pi, and 2 pi. So those are the standard graphs that you should already know, and all you are doing is sketching them, but instead of sketching them in degrees, you're sketching them in radians. So we can use the base graphs for trig to do some trig. sketching of graphs, but this time in radians. So again, we're just recapping the work we did on transformations. So the first one, y equals cos of 2x. Well, you know that is a stretch. Scale factor a half in the x direction. So whereas the wavelength for a cos wave is usually 2 pi in radians, the wavelength for cos of 2x would be pi. So you get 2 waves into 2 pi. Number 2, again, transformation is a translation of positive pi in the x direction. And again, you can use your base waves to help you to sketch that. Number 3, this is 2 transformations. So first of all, it is a translation of minus pi over 2 in the x direction, followed by, you can see the negative at the front of the trig function, so that is a reflection in the x-axis. And question 4 again is 2 transformations. First of all, and it doesn't matter which way around you actually do these, so it's a stretch, scale factor 2 in the x direction, followed by a reflection in the y-axis. And again, if you stop the video and you do your sketches following the basic transformations, and then you can check your answer with the model solutions. As we've said, anything that we could do in degrees, we can do in radians. So here's a question, right angle triangle ABC. You can see that the hypotenuse is 15 and you're given an angle of 0.67 radians. You can see the little superscript r, and we want to find BC. So we're trying to find BC, we're trying to find this one, which of course is our opposite. We're given the hypotenuse, so it's basic trigonometry, so you can write the sine of 0.67 equals opposite, which in this case is x or BC, over hypotenuse, which is 15. So x equals 15 sine 0.67. When you pop that in your calculator, you will get your answer, which is therefore the length BC equals 9.3147, and that goes on. So BC equals 9.31 centimetres, and that's correct to 3 significant figures. Our second question is a non-right angle triangle, and this one I'm going to let you do on your own, and you can see that you have non-right angle triangle. Your angle is 1.25 radians, one side of 16, one side of 9. So in order to find side AC, you're going to use the cosine rule, because you've got two angles and two sides and the included angle. But make sure that your calculator is in radians. And the area of a triangle, remember the formula for the area of a triangle is half, and then it's the sides we've got. So in this case, it's going to be BC times AB times the sine of 1.25 radians, and that will give you the area of your triangle. Again, if you then stop the video, work those out yourself, and then check those with your model solutions. And that is the end of the video for 5.1.